Presentation is by Anais Jacob. And the topic is neutron diffraction and neutron imaging techniques for residual stress measurement of welded.
Good afternoon, everyone. My name is Anais Jacob, and I'm doing my PhD at Cranfield University with the Renewable Energy and Marine Structure Center. And I'm sponsored by the Science and Technology Facilities Council in the UK. So today I'm going to talk about the neutron diffraction and neutron imaging residual strain measurements on offshore wind monopile weldments. So here's the outline of my presentation. So I'm going to talk about the focus of this study, the specimen design and extraction, the general test procedure with the setup on NGINX and IMAT, and the results and discussions. So renewable energy resources play a key role to mitigate greenhouse gas emission and provide energy security. Wind energy is increasingly becoming one of the preferred sources of energy, especially in Europe, with the potential for larger scale applications. One of the most important challenges in the offshore wind industry is the assessment of the structural integrity of the foundations, which are becoming one of the largest engineering structures in the sector. So welded joints are widely used to support offshore wind turbines, and during the fabrication process of the monopiles, a significant amount of residual stresses is generated and have a substantial influence on the structural integrity and fatigue life of the components. In order to accurately characterize the service life of the monopiles, residual stresses should be measured and quantified. So the focus of this study is to use the neutron diffraction and neutron imaging techniques to measure the locked-in residual strain in compact tension specimen extracted from monopile weldments. So just to give you an idea, this is a picture of an actual wind turbine, the monopile of an offshore wind turbine. And here is the size of a human being, just to give you an idea of the size of the monopiles. So S355 J10 plus M structural steel is used in this study and is widely used in the fabrication of offshore wind turbines, monopiles. Multipass submerged arc welding technique was conducted on a double V groove plate with no post-weld heat treatment, so that's this picture here, in order to replicate real-life conditions. And we're talking about the weld in this region, as it's been proven that the crack initiates within the HAZ of the circumferential welds. Compact tension specimen have been extracted from 16mm thick slices from the welded plate with the notch tip located within the HAZ, as you can see here. And this is a picture of the final compact tension sample after polishing and etching, in order to locate accurately the heat affected zone. So regarding the general test procedure, residual strains have been measured on one of the extracted compact tension specimen using neutron diffraction and neutron imaging techniques on NGINX and IMAT at the STFC. So neutron diffraction measurements provide residual strain in all three directions, while neutron imaging only gives the longitudinal residual strain in the chosen experimental conditions. So here is a schematic of the neutron diffraction setup, and this is neutron imaging. So measurements have been performed before pre-fatigue cracking. So regarding the neutron diffraction measurements on NGINX, so we also extracted thin 4mm slice from one thicker compact tension specimen in order to draw small cubes of 3mm cubes for the D0 measurements along the crack path. So I'll just show you later where we use the D0. And a gauge volume of 2x2x2 was also used to measure the residual strains at mid-height and mid-thickness of the sample. And finally, a rotation of the sample by 90 degrees was achieved in order to obtain residual strains in all three directions, so transverse, longitudinal, and normal. So here we've got a picture inside engine X. So the neutron beam is coming out this way, and we've got the compact tension specimen sitting between the two collimators. So for the neutron diffraction data analysis, the time of flight is measured when the angle of scattering is fixed, and the lattice deformation is measured following the Bragg slope, as described in this equation. And then the residual strains can be calculated using the following equation. So this is where the D0 is used. Regarding the neutron imaging measurements on IMAT, so this is the technique which was used to produce 2D radiographies of the sample. And the image were directly produced by transmitting a neutron beam coming out this way onto a specimen here, and onto a microchannel plates detector here. So in neutron transmission, the experimental setup is such that the Bragg angle is equal to 180 degrees. And here, just to show you, we've got a sample in front of the MCP detector. So for the neutron imaging data, they were analyzed using a Python script that I developed with my sponsor, the STFC, and where the transmission law was implemented. And we also used an image processing software. And the results are quite sensitive to the region selected for the analysis. So it's quite a dark picture, but in red, just here, along this line, we've got the HZ, so that's the region selected for the analysis. And here is the results. So it's a map of the wavelength. So a sensitivity analysis has been performed with respect to the D0 values chosen. And the following cases have been compared. So first we use the D0 values from the neutron diffraction measurements. Then a single D0 value taken as the average of the neutron imaging measurements within the HZ. And then a single D0 value taken from the strain balance through thickness in longitudinal direction. And finally, a single D0 value taken from the corner of the sample. So I'm talking about these corners. So corner 1 is within the weld metal, and corner 2 within the base metal. So just to mention that the corner taken for the D0 measurements are not the actual corner of the sample. Due to the size of the MCP detector, we could only image a portion of the sample. So now the results. So only the residual strains are presented here, as we were not able to get the other two directions with the neutron imaging measurements. So the main difference between the neutron imaging and neutron diffraction is that the neutron imaging is a volumetric measurement applied on a plane to measure the residual strains in a direction normal to the plane orientation. And the neutron diffraction provides the residual strains along two directions at a specific point. So on this graphic, in a dark blue color here, we can see the neutron diffraction in longitudinal direction, so that's this curve. And the other four are the neutron imaging results using different D0 assumptions. So the purple one and the green one, using the D0 as the average of the neutron imaging measurements, and the D0 as the strain balance, are sitting on top of each other. And the bright blue, so this one, uses the D0 from the corner 1. So if you remember, the corner 1 was taken within the weld metal, and the red one uses the D0 from the corner 2 within the base metal. So the neutron imaging residual strain results generated using different D0 assumptions follow all the same trend. We can also conclude that the location of the corner for the D0 values seems to influence the analysis. Corner 1 may include non-strain-free conditions, as it's been taken within the weld metal. And like I said, the residual strain trends fall on top of each other when D0 is taken as the average of the neutron imaging data in the HZ region, and when D0 comes from the strain balance in through thickness direction. And finally, all these results are in good agreement with neutron diffraction measurements. So in conclusion, we presented a comparison of the Newton diffraction and neutron imaging measurements on a compact tension specimen extracted from an offshore wind turbine monopile. And we also performed a sensitivity analysis in terms of the neutron imaging data analysis. So I just wanted to mention that further fatigue crack growth tests in air and in seawater environments are being performed in order to assess the fatigue life of the component in the presence of residual stresses. Thank you.
Thank you very much, Ms. Jacob. Since we have 5 minutes extra, you can have your questions from Ms. Jacob if you have. Is there any question related to this presentation? No question? Yes, yes please. If you use the microphone.
What we have found several times was that we didn't have residual stresses at the jaw of the weld. In the weld and in center line there are high tensile stresses, even a little bit tensile stresses in the surrounding of the weld, but at the jaw there are almost no residual stresses. Do you have made such an experience? Or?
What we actually observed is that we have a true thickness distribution of the residual stresses. So that's another thing I didn't mention here. And here I presented the longitudinal residual stresses. So sorry?
Not transverse. If you have a crack in the weld jaw, then the transverse residuals you don't have.
Yeah, I totally agree. So the transverse residual stresses are presented using the neutron diffraction that I couldn't present here because I just wanted to compare the neutron imaging and neutron diffraction measurements. But with the neutron imaging technique, I couldn't get the transverse residual stresses because I wouldn't need to translate the sample. And then it's just too thick for the neutrons to go on through the detector. That makes sense.
Thank you very much. Your question? Yes, please.
Yeah, I want to ask a small question because normally if you cut a specimen from the big specimen and then the stress is really skewed. So the relief of the residual stress need to be considered in your measurement. So in your case, have you think about this problem or you just want to measure the CT specimen?
So we've done another, we published a paper on this exact topic actually, and we've done some contour measurements on the actual plate, and we compared the residual stresses within the plate and with the compact tension. So right here, right now, yeah, it's just the compact tension, but behind that we've done some contour measurements.
Thank you very much. If you have any more questions, you can ask them at the end of the session.